First one. Nail backwards.
I don't know how to worry about this.
Yeah, why do it?
It has to be a number that can multiply by itself. Like,
What number is it?
That makes sense.
because a square is multiplied by
All right, folks. Should we talk about it together? Why do we call it squaring a number? So, for instance, when I have the number 5, to the power of 2, we don't normally say 5 to the power of 2. In fact, most people don't say 5 to the power of 2. Most people say 5 squared. So why do we say 5 squared? Why do we use the word square? Why not quadrilateral? Why not kite? Why not rhombus? Why not tetrazoid? Like 5 trapezoids. Why don't we say that? Why do we say square? You don't know? I suppose it's etymological, historical, linguistic, why we say square as opposed to any other word. Is because what if you wanted to find the area of a square whose side length was 5? What is the area of a square whose side length is 5? What's the formula for area? Length times width. And in this case, it's a square, so it happens to be the same number twice. So then 5 times 5, which could be represented as 5 to the power of 2. And since we're finding the area of a square, we say 5 squared. Like literally, you take a marker that's 5 inches long, you take another marker 5 inches long, and you make a square out of it. So you're taking a number and you're turning it into a square, but you're calculating its what? Area. Yeah, so we refer to 5 squared because that's how you calculate the area of a square whose side length is 5. So when I say anything else like 9 squared, what am I really talking about? Talking about a square whose side lengths are 9 and whose area therefore is 81. So historically that's why we call it squaring. So 5 squared is 25, and we use the word square because we're calculating an area. Okay, what about this? Do we say 5 to the power of 3? What do we say? 5 cubed. Why do we say 5 cubed? What are we calculating now? The what? What are we calculating now that it's 5 cubed? Are we calculating the area of a square? What are we calculating? Volume. The volume of a cube now. So now if you look at a cube whose side lengths are all 5, 5, 5, and 5, then the volume, which is length times width times height, is really 5 times 5 times 5, which is 5 to the power of 3. But just to make it short and snappy, people say 5 cubed because they're referring to a cube. So now we have volume. And so area is a 2-dimensional thing, volume is a 3-dimensional thing. So what do we call 5 to the power of 4? What do we call 5 to the power of 4? Nothing, because we don't live in a 4-dimensional universe. We sad creatures that we are live in a 3-dimensional universe. That's all we got is 3 dimensions. So we only have fancy names for the 2 and 3, but we don't have one for 4. But if we were 4th-dimensional creatures, don't you think we would call it by a name there? We would. And so in fact, a 4th-dimensional, so 2D squared, 3D cubed, it's called a 4th-dimensional hypercube. I can't really do it justice. It's actually very, very challenging, I find, to draw, to draw a hypercube. It would look something along the lines of this-ish. I mean, this is just a terrible drawing. There. That's what a 4-dimensional hypercube would look like, kind of. And then we would call this the hypervolume of a 4th-dimensional hypercube. And so that, well, I never even answered that. 5 times 5 times 5 is 125. And then 5 times 5 times 5 times 5 is 625. So 625 would be the hypervolume of a hypercube in fourth dimensional space. And we would call this 5 hypercubed. 5 cubed, 5 squared. Okay. Now I know you think I'm just being cute, but really that's what we would call it. Because that is actually the name of a hypercube, and that really is hypervolume, that's the name of it. So that's 5 squared, 5 cubed, 5 hypercubed, and we're referring to calculating area, volume, and hypervolume. Okay, so going back to the beginning, what is it? Why do we call it squaring a number? What are we actually calculating? Area. Area. We're actually calculating area. So what does it mean to square a number? Sorry, I went out of order. What does it mean to square a number? You just multiply it times itself. And in what context do you multiply a number times itself? Finding the area of a square. Finding the area of a square is when you multiply a number times itself most naturally, and so we call it square. So what does it mean to square root a number then? Right, like we've got, here. We have a square, a cube, and a hypercube. What does it mean then to square root a number? Like, as an example, let's say I wanted to do the square root of 9. What's the square root of 9? 3. So what does that mean in context? Yeah, find a number that when you multiply it times itself, you get 9. So what is the 9 and 3 in this situation? Which one is the area? Which one is the side length? Yeah, the 3 is the side length, and the 9 is the area. So when you square root a number, what are you doing? When you square root 9, you're saying 9 is the area, and you're trying to find the side length of a square whose area is 9. So here's how you can write these two formulas, folks. You could either say, I don't have a good place to outline it right here. You could either say area is equal to side length squared. That would be the formula for the origin of the word square. We're saying that the area of a square is the side length times the side length. Or you can say the square root of area is equal to a side length. That's what you're saying. You take the area of a square and square root it, that's going to tell you the side length. I would probably write that down somewhere. I don't know where. I mean, you could always just do it at the top of your packet called squares. But historically, it would be really cool if you guys all wrote it down. You've got the area equals side squared. You've got the s on the side and on the side. These facts right here, they go really well together. So when we talk about squaring, we're talking about finding the area of a square, which is length times width, but since they're the same, it's just side times side, which is side squared. And so you're talking about a square whose area is a, whose side length is s, and then you have these two facts that speak the truth about it. So either the area is side squared, or the square root of area tells you the side. So who'd like to try that one out for us? Tell me a whole story about this. What are we really describing right there when we say find the square root of 36? Anyone want to try? Given everything that we just said over there? Especially in the blue. What am I really describing here? Go ahead, Jasmine. What? 36 is the area. Yeah, we have the same number on both sides. And so the side length is? Yeah. And so the answer is 6. So that would be the fact. The square root of 36 is 6 because 6 squared is 36. But also, if the area of a square is 36, then the two side lengths are both 6. So that's one way you could say it. Another thing you might want to keep in mind is that when we say the square root of 49, what is the square root of 49, everybody? 7. You could say the square root of 49 is 7 because, and this is very helpful to follow it up with a because statement, because 7 squared is 49. And you'll notice those two facts go together, right? These two facts are the related facts. You can either say the area of a square whose side length is 7, the area is 49, or you can say if you're looking at a square whose area is 49, then one of those side lengths is 7. Well, both of those facts go together. Okay, last question up there. Why does a square root have two answers? We haven't talked about that yet, but what's the square root of 25? 5 or -5. Why are there two answers?
You squared -5.
Yeah, exactly. Because, again, the because statement, the square root of 25 is 5 because 5 squared is 25. And also because if you square -5, that's also 25. So there are technically two answers. And the way we write that down, we're always going to write it down as the square root of 25 is plus or minus 5. We haven't used that symbol in this class yet, have we? Or have we? Yeah, we have, haven't we? We've been talking about plus or minus? Wait, seriously, have we? We haven't used that symbol? Okay, so plus or minus just means that both of them are possible answers. Now, in the context of area, do both of those answers make sense? No. You could definitely have a square whose side length is 5 and 5. But can you have a square whose side lengths are -5 and -5? No, that doesn't make any sense. And that solution would be called extraneous. Yeah. So numerically, there are two answers. In the context of a word problem, there's probably only one answer. And typically, we take the positive root. I think we call that the primary root, the one that really matters the most. So sometimes a problem will only be interested in the positive square root because that's the one that would make sense in a word problem. But sometimes we're interested in both of them. Okay, boy, that's a lot in just one little word, square, and where that word came from. All right. So coming up, here we are, folks. We have 4 class periods to get through chapter 9, which is all about square roots, well, squaring and square roots. I'll tell you right now, there are lots and lots and lots of rules. So maybe you want to have an extra sheet of lined paper out next to your notes packet where you're just writing down rules as you go, because there will be quite a few of them. So here we go, chapter 9. I have a joke to start us off. Wait, I already told you those jokes. What was the joke I told? Tell you that. Aha! Why did the bicycle fall over? Why did the bicycle fall over? It was too tired. Everyone was really impressed by that joke, I can tell. All right, warm-up material. Everybody take out this sheet right here. The first thing now this is just for practice. I'm not collecting this, but I would write it all down. The first thing I gave you was all the square numbers 0 through 400. So where did all those numbers come from? What are these numbers? So they're square numbers. So for instance, that's 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, all the way up to 20 squared. I imagine most of you have memorized through 100. You might also have memorized 11 squared and 12 squared, maybe 13 squared. But after that, it tends to drop off a little bit. Like, did you know that 17 squared was 289? Maybe, maybe not. Well, I really encourage you to write this list down and start memorizing it. You want to be familiar with these numbers. That if you were just walking down the street and you saw 324, you'd say, oh, look at that, 18 squared. Right, so you want to build some familiarity with these numbers. What I would probably do is write them on your forearm, like here. That way you can look at it over and over again for the next couple of days. Makes for a really nice tattoo. Wouldn't that have been cool if I had already had it? Oh, I should have already had it there on my forearm. That would have been wild. All right, so yep. You can practice memorizing those numbers and just saying them. You can even, okay, so later today, you're waiting in line for food, you're driving in traffic. Just start counting out your numbers if you're driving, and you can say 1 squared is 1, 2 squared is 4, 3, 9, 16, 25, 36, 49, 64, 81, 100. And just start counting on your fingers, and then see if you can go beyond it as well. Okay, so that's why I gave this to you, and now you can practice as well. So later today, go home, pour yourself a nice tall glass of iced tea, and practice knowing those answers off the top of your head. Okay? That's the whole first page. You can turn the page. It's just practice. This next page starts to build your relationship between square roots and squares. So go ahead and start filling out this number line with me. I'm going to draw mine at the top here. what we want to do is above each number on the number line, we're going to write in the associated square root fact. So, for instance, the square root of 9 is equal to 3. And the square root of 16 is equal to 4. And the square root of 25 is equal to 5. And so on. You're going to go across that whole line there and write in all of the associated square root facts. So the start of your number line would look like this. Root 0, root 1, root 4, root 9, root 16, root 25, all the way across. Again, this is going to help you build familiarity with these numbers so you can start memorizing them, build a friendship with them. Keep in mind that as you write this number line, because I've asked a lot of students to do this in my life, and a lot of them just start writing the numbers, 36, 49, etc. Is that technically accurate to say that the number line, that this number right here is equal to both 6 and 36? Right. That's not technically accurate. 36 is not equal to 6. You need to have the square root symbol on the 36. Now this is technically accurate. The square root of 36 is equal to 6. Those are the same numbers. So you have to put the square root symbol above them. We're trying to say this is a number line, and that's where those square roots are actually located on the number line. Okay, so once you do that, again, that's just more practice, getting this muscle memory in your hand, so you're memorizing these numbers. And then you can go down below and actually practice doing all of those square roots. I'm not collecting this for a grade. You won't get any points for it, but your life will be better for it if you practice it a little bit so that you're gaining more familiarity with these numbers. Okay, well, that's it for that page. Can we turn the page? This is all just practice for you to go home and try it out. All right, this is a skill that we'll go ahead and practice right now. This is a really important party skill. You see up at the top I wrote critical math party skill. So let's say you're at a math party and you're just bumping elbows with people, talking, chit-chatting, having a nice time at this math party you just went to, and people are doing square roots. And someone's like, hey, what's the square root of 100? And you're like, that was overwhelming, folks. What's the square root of 100? 10. 10, all right. And then someone says, what's the square root of 64? 8. And then someone says, what's the square root of 85? Okay, very good guess. Sarah says 9.4, right? At that point, is there a square root of 85? I mean, it doesn't come out clean, does it? It does not come out clean. So let's try this together. I'll just have to rewrite that over here. So I say here, all the square roots from root 81 through root 100 are located somewhere between 9 and 10. So start labeling that with me. Here's my number line. I just zoomed in just to look at the numbers 9 and 10. And right above 9 and 10, we're going to write in root 81 and root 100. Because those are the associated square root facts. And then we're going to draw what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You've already got your tick marks there. And so let's think about what happens between root 81 and root 100. First of all, on the bottom, we could put in some decimals. This would be 9.1, 9.2, 9.3, 9.4, 9.5, 9.6, 9.7, 9.8, 9.9. Our goal is to, off the top of your head, be able to square root any number to 1 decimal approximately. So now that we have this little spectrum here, we could go ahead and talk about any square root between root 81 and root 100. So let's try it. How about consider the square root of 82? Where's the square root of 82 up here? It's like right there, right? So roughly speaking, the square root of 82 is 9.1. You know, and you could just say that. You just flippantly say, oh, you know, it's like 9.1. You know, you're not trying to be accurate, you're trying to be close. Okay, what about the square root of 90? What's the square root of 90? Well, where would root 90 be? Probably right around here, right? Just somewhere in the middle. So the square root of 90 is? 9.5. Yeah. And then what about the square root of 98? What would the square root of 98 be? Be right over here somewhere, right next to root 100. So that answer would be 9.8, 9.9. You can say either one of those. You're just trying to approximate it. All right? So everybody, let's try this a little bit. This should theoretically be a little fun. So root 83. I'm going to start in the back there with Manuel. No, I'll start with Jesus. Manuel, you're next. Manuel. Jesus, what's the square root of 83? What's the square root of 83? Very nice. 9 by 2 sounds great to me. What's the square root of 89, Daniel? 9.4 sounds great. Yeah, sounds good. What's the square root of 97, Lilia? 9.7 sounds great. What's the square root of 85, Jackie? Yeah, 9.3 sounds pretty good. What's the square root of 92, Jasmine with an S? Yeah, maybe 9.6, something around there. What's the square root of 87, Martha? 9.4 sounds good. What's the square root of 95, David? I feel like 9.7 sounds about right. And what's the square root of 80, Eduardo? Ooh, this is a tricky one. What's the square root of 80? Yeah, 8.9, really nice. That was off the spectrum. It was to the left of it a little bit. And then what about the square root of 101, Chris? Yeah, 10.1, very nice. Now, folks, the key of doing this critical math party skill is you're just coming up with a ballpark approximation. So let me demonstrate here. The square root of 90, an acceptable answer for the square root of 90 is any of these. 9.5, 9.4, 9.6, 9 something. You could even just say 9 something if you wanted to. But what you couldn't say is 9.1, right? If we're looking at the square root of 90, would it be appropriate to say 9.1? No, that's a bad guess, right? That's nowhere close. So you just want to be close in the neighborhood. The goal is to approximate the answer and sound like casual about it. Like, oh, you know, square root of 90 is like 9.5, right? You want to sound casual and confident and close, right? So that's the whole point of being able to square root a number in your head. Okay, well, that's it. You can continue practicing that. Down there at the bottom, I gave you another square root number line. I don't think I put any more up here. No, I didn't. But, you know, let's just do the first one on the list. No. I'm going to say, I'm just going to make one up. What do you think the square root of 30 is? The square root of 30. What do you think the square root of 30 is?
Like 5?
Yeah, like 5.5? That's about right. That sounds really good. That's all you'd have to say. What's the square root? Here's a trickier one. What's the square root of 5? The square root of 5. Maybe 2.2, 2.3, somewhere in that region. Now, of course, you can always type these into your calculator, but the point is to be cool and hip at a party and be able to square root these things off the top of your head to 1 decimal. Now, if you wanted to be funny, and someone said, what's the square root of 90? You know, someone says, what's the square root of 90? If you're trying to be funny, you say 9.57632. Right? Because no one can do that many decimals off the top of their head. People would know that you're just being funny, right? Because nobody can actually do that in their head. You're just supposed to give 1 decimal. Okay. All right, so that's critical math party skill, approximating to 1 decimal. Next, now, simplifying roots. I'm not sure if you've ever done this before. Maybe you have, maybe you haven't. It's another very important skill. And the word simplifying begs to be defined. What does it mean to simplify? To do what? What does it mean to simplify? What is it, Daniel? Combine? Okay, maybe like if you have a bunch of terms and then you combine like terms, you could call that simplifying. What else does simplifying mean, David?
Take square number, it's the most prime number.
Oh, maybe somehow get it to its prime number? Yeah, something like that. Do you mean prime, like 5 is a prime number?
Yes.
Okay, maybe to break it down to primes. What do you think, Adiana? What does simplifying normally mean? To reduce it? And what does it mean to reduce something? Okay? To get to its lowest term or make it smaller? So for instance, folks, what if I told you to simplify the number 5/10? What is the simplification of 5/10? 1/2, right? What is simple about that? We just said we simplified it. What's simple about it? The numbers are smaller, right? I mean, that's it. That's all we mean, right? We just want the numbers to be smaller. Just as a nice example, if you were going to a math party and people asked you, hey, what'd you have for dinner last night? You're like, pizza. They're like, really? How much pizza did you have? And you were like, 17/34, right? That would be considered very rude, Like, why would you go communicating with your friends? I ate 17/34ths of a pizza last night. What does 17/34 simplify to? A half. You know, you would just say a half. You know, saying 17/34ths is just rude. So simplifying means boiling it down to the smallest possible numbers, the simplest relationship possible, which makes communication to your audience and your friends better. Okay, so what on earth can we possibly mean then about simplifying these roots? We want to simplify them. That doesn't mean approximating to 1 decimal, right? Root 20 would be like 4.5, and root 63 would be like 7.9, and root 80 would be like 7.9. Did I just say that twice? No, it says 7.9 and that's 8.9. Anyway, we're not talking about that. That's approximating to 1 decimal. I want to simplify the root. So, any thoughts on what that means to make a root smaller? This could be a brand new skill. Maybe you've never seen this before. So let's start at the top, folks. It says first you need to know the difference between a square number and a non-square number. Why are these square numbers? What are they equal to? Like, what's 100? 10 squared. And what's 121? 11 squared. So square numbers are equal to some whole number squared. These are non-square numbers. Why are they not square numbers? Nothing times itself equals these numbers. That is, no whole number times itself equals 2. No whole number times itself equals 3. So these are non-square numbers. So first, knowing the difference between a square number and a non-square number. Now, you need to know the product rule. So everybody right here, just off to the right, write that down again in your own handwriting. Here's the product rule. The product rule states that if you have, I need better pens. If you have the square root of 2 numbers being multiplied together, then that's actually equal to the square root of the first number times the square root of the second number. And we call this the product rule for roots. So let's see an example of why this is obviously true. Consider the square root of 36. Everybody, what's the square root of 36? 6. Now, how can I rewrite 36 as the product of 2 numbers? In a lot of different ways, right? 36 can be written in a lot of different ways as the product of 2 numbers. Just to review a factor table, if I have 36, that's really 1 and 36, 2 and 18, 3 and 12, 4 and something, 9, 5, 6, and 6. I'd like to rewrite 36 as the product of 2 numbers that are both square numbers. Which ones? I want both of the numbers to be squared. Is it 4 and 9? 4 is a square number, that's 2 squared. 9 is a square number, that's 3 squared. So 4 and 9, I'm going to rewrite this as 4 times 9. And now this is the product rule. I get to break that up into root 4 times root 9. And now what's the square root of 4? 2 and the square root of 9? 3. And 2 times 3 is 6. And is that what the square root of 36 is? No. Now, the product rule for roots is used by mathematicians to look impressive. All right? It's used by mathematicians to look impressive. So let's say that we wanted to do the square root of 12,100. Right? A mathematician, you know, they'll pull that off in their head and you'll check it with your calculator and be like, whoa, she knew what it was. How'd they do that? But is it impressive that they could square root 12,100 in their head? It's not. Because how could I rewrite 12,100 as the product of 2 square numbers? What 2 square numbers multiply to make 12,100? Yeah, is it 121 and 100? What's 121 times 100? 12,100? Okay, so everybody, you would take that, break it apart into 121 times 100, which is root 121 times root 100. And the square root of 121 is 11, and the square root of 100 is 10. 11 times 10 is 110. And it's not that impressive. So that's how mathematicians square root gigantic, huge numbers by just breaking it down into smaller numbers that they can square root. Is that bad that I just showed you the magician's trick? Like, is magic less impressive once you know how they did it? Or I don't know. All right, well, that's how they do it, folks. So that's called the product rule. We're going to use the product rule to simplify square roots. So everybody, you're normally not this lucky. Okay, normally it's not going to be like this, where you can rewrite a number as the product of two square numbers? Normally, there's just going to be one square number and one non-square number. So everybody, let's try it out right here with root 20. How can I rewrite root 20 as the product of a square and a non-square number? What square number goes into 20? It's 4. Now, I'm going to show you the technical method here. The technical method is you find where 20 would be. Is that where 20 would be? And then you work your way to the left, dividing by every number. So, is 20 divisible by 16? No. Is it divisible by 9? No. Is it divisible by 4?
Yes.
Yes. So you take the first square number that goes into that number. So, we're going to rewrite 20 as 4 times 5. Go ahead, you got the space there. And then you'll use the product rule for roots to break that up into root 4 times root 5. And then you'll be able to simplify the first one. You can simplify the first one. So what's our answer? 2 root 5. Now you might look at 2 root 5 and say, gosh, 2 root 5. Is root 20 really equal to 2 root 5? Is the square root of 20 actually equal to 2 times the square root of 5? Everyone take out your calculator and let's check. Is the square root of 20 really equal to 2 times the square root of 5? My calculator is dead. So I'm going to have to trust you folks. What's the square root of 20? We say it a little louder?
4.4721335.
All right, that's good. So the square root of 20 is really 4.4721335. Now, folks, on your calculator, do the square root of 5, enter, and then times 2. On some of your calculators, you can just type that in directly. You can just type in 2 root 5. But for some of you, that doesn't work. You'll have to type square root of 5, enter, then times 2. And Sarah, what's the answer?
The same thing.
The same thing. So folks, the square root of 20 and 2 root 5 really are equal to each other. They're the same expression. No, they're the same value. They have the same value. They look different, but they represent the same decimal. In much the same way that 17/34 and 1/2 look different, right? They look different, but in fact, they both represent the same decimal value of 0.5. So these look different, but they both, in fact, express the same value. And we call this one simplified. Why do we call it simplified? What's simpler about it? It's a smaller number inside the root. That's what we cared about. Because after all, this one started with 1 root 20, and now we changed it to 2 root 5. So the number in the root got smaller. The number outside the root got bigger. But the number inside the root got smaller. And that's preferable because we humans across the board despise square roots. Whenever humans can get away with not using a square root, they would prefer to. I don't know why it is, it's just true. People don't like square roots. So we call this simplified because the number under the square root got smaller. Okay, so folks, try another one. Do root 63. Let's use that same method. You look at 63, you find where 63 would be, which is right there, and then you start working your way to the left, dividing by every number as you go. So does 63 divide by 49? No. Does it divide by 36? No. Does it divide by 25? No. Does it divide by 16? No. Does it divide by 9? Yeah. So that's the number you choose. And you say root 63 is really root 9 times 7, which is really root 9 times root 7. And then that's just 9 root 7. And we call that simplified. Keep in mind, folks, that we now have 3 different ways to represent a number. We could represent it as the original square root, root 63. We could represent it as a decimal approximation to 1 decimal, 7.9. Or we could represent it as the simplified version. All 3 of those numbers are all trying to represent the same value. But we call this one simplified. Okay, well, root 75, let's try that one. Oh, come over here. Root 75, what square number goes into 75? This one you might all just know off the top of your head. What square number goes into 75? 25. 25. But again, you use the method. you'd find where 75 is or would be, and then work your way to the left, dividing by every number until you hit one that actually goes into it. So root 75. Now you might get to the point where you don't feel the need to rewrite it as 25 times 3 and then write it again as root 25 times root 3. You might feel like you can just go straight to that. Right? Is that fair? Because writing that twice, I mean, that's just a formal demonstration of the fact that you're using the product rule. If you wanted to, you can just go from root 75 straight to root 25 times root 3 and be done. Well, I mean, you still have to simplify. Yeah, but you could do that in just 2 steps instead of 3. And I'll give you full credit. I'll give you full credit for that. Now, folks, the next one is a little more challenging, root 72. What square number goes into 72? Well, darn it, yes, that's true. I was expecting most people to say, what square number goes into 72? 9, right? And in fact, there are 2 different square numbers that go into 72. 9 and 36. In fact, there's 3 numbers that go into 72. 4, 9, and 36. Is that correct? Does 4, 9, and 36 all go into 72? Yeah. So which one should we use? 6. The biggest one, because the method is you look at where the number would be and work your way to the left. So now let's just say you didn't know that 36 went into 72 off the top of your head. What do you actually need in order to do this procedure? You need your calculator out, right? You need your calculator out, and you'll just sit there and you'll say, okay, 72, start dividing. 72 divided by 64 is a decimal. 72 divided by 49 is a decimal. 72 divided by 36 is 2. And then from your calculator, the fact that you divided and you got a whole number, then you would say, okay, root 72 is really root 36 times root 2. And then the answer is 6 root 2. So you absolutely need your calculator out, because some of these numbers are so big that it's not obvious. It's not obvious what square number goes into it. Which is another reason why I said you should write all those numbers down on your forearm for the next day or two so that you have it there as an immediate reference. You can just look and see all of your square numbers. Okay, well, I think that's all I have to say about that. We will use that skill throughout the chapter. So now you have this page, you can practice. I'd say the most important thing is keeping out your list of square numbers until you have them memorized. Okay, any questions about that? I have 2 questions for you. What would have happened had we done the square root of 72 as 9 times 8? Because 9 also goes into 72. What would have happened there? Can we do it? That would be root 9 times root 8, which is what? 3 root 8? Are we done?
No.
Did that give us the same answer? It didn't. Why not? Because you can still simplify root 8. See, this is crazy and kind of weird. But just like with fractions, you know how with fractions, like if you had 12 24ths, you could simplify that a little, like dividing by 2, and then you'd have 6 12ths. And then you could divide that a little more, and then you'd have 3 6ths. And then you could divide it a little more, and then you'd have 1/2. But of course, what would you rather do? You'd rather just go straight there, right? So you're looking for the biggest number that can divide into 12 and 24, so you simplify in 1 step. Likewise, 72, the biggest square number that went into it is 36. So you'd want to use 36 because it's the biggest square number. What do I have to do now? Now I have to simplify root 8. So I look at 8 and I say, 8 is here, start dividing my numbers to the left, 8 is divisible by 4. So now I'd have to rewrite this as 3 root 4 root 2, which root 4 is really 2, and then 3 times 2 is 6 root 2. And then I get the same answer. All right? So when you simplify a root, you want to find the largest square number that divides the given number. Okay, finally, how do you simplify this? What square number goes into 15? Well, that's true. 1 does. Is this helpful? Did we do anything? No, we didn't do anything. So can you simplify root 15? No. So what do we say? You could say already simplified. Or you could say can't be simplified. Between the two of them, already simplified or can't be simplified. I like the phrase already simplified. It sounds optimistic and positive. Like, yeah, that one's already simplified, right? It's like, it can't be simplified. So this number is already simplified. What else was there to say about it? Okay, I guess that's it. Okay, had you folks ever done this skill before? Simplifying a root? Maybe, maybe not, okay. Well, there we have it. So down below, you've got a lot more practice to do. Again, you can just go home, you know, hang out, practice a little bit, just to gain a little more practice. Okay, all right, let's go to the chapter 9 practice backup. Now, folks, everything we just did was really just scratching the surface. We really just scratched the surface about the types of skills that we're going to learn in this chapter. So what did we just learn? We learned how to approximate a root. So such as root 72. Root 72 is roughly what? What's the square root of 72 is 1 decimal? You can look at your number line, you all still have it right in front of you. What's the square root of 72? 8.5. 8.5 sounds pretty good, right? Because 8 squared is 64 and 9 squared is 81, so I'm going to say 8.5. So that's approximating a root, but then you also have simplifying a root. All right, so we have those two different skills that we just talked about. Okay, so chapter 9 is going to be all about square rooting, but not just square rooting. It'll also be about cube rooting and fourth rooting and fifth rooting and anything else that you might be able to do with a root symbol. All right, any questions before we get started? You know, like a question you've always wanted to ask about square roots. You know how sometimes you lay awake at night and you can't fall asleep because you're thinking about square roots? Anyone have? Vanessa? Oh, it's really helpful. Okay, well, folks, when you square root a number, there are two answers, plus or minus. Why is that? Here, I'm just going to call on somebody. Why are there two answers? Daniel? Exactly, because a negative times a negative is also a positive. So if we're going to go ahead and start looking at, say, number 1, the square root of 169 is plus or minus what? 13. Because, and this because statement's always nice to throw in there, 13 squared is the same as negative 13 squared, which are both equal to 169. Because a negative times a negative is positive. Okay, how about number 2? When you square root a fraction, what do you do? So I want to square root 25/256. How do I square root that? Yeah, you do the root of the top and the bottom independently. And in fact, that is what I said right there, right? You square root the numerator and denominator separately. So you would do the root of 25, and then the root of 256, and you calculate both of those separately. I bet we all know root 25 is 5. What's the square root of 256? It's on the number line. Have your number line out in front of you. 16. So that's plus or minus 5/16. The answer is plus or minus 5/16. Now, on the other hand, number 3, if they ask you for the square root, like if they say what's the square root, they mean the positive one. So in the case of 3, 4, and 5, root 144 just means 12. That is if the instructions say find the square root. Likewise, negative root 100, well, just pretend that negative isn't there real quick. What's the square root of 100? 10, but there's a negative sign in front, so the answer is negative 10. That's how they would ask for the negative root, is they would put a negative sign in front saying, hey, we specifically want the negative root. And then how about this last one, root negative 256? Type it in your calculator. What's the square root of negative 256? Yeah, it's error. undefined. No solution. Or maybe your calculator says imaginary. It's a lot of different options, huh? Why does the square root of negative 256 not have an answer? Yeah, because anything that you square is going to become positive. If you know, if this because statement, let's say you said the answer was 16. 16 times 16 is positive 256. And let's say you said the answer was negative 16. Negative 16 times negative 16 is still positive 256. And so in fact, there's no number in the universe that if you multiply it times itself, you get negative 256. And that's because a positive times a positive is positive, and a negative times a negative is positive. So this just has no solution. And in fact, I just realized that I should have shared a little bit more information. You still have a lot of space over here, right? What numbers were those? Oh, they were up there. They've done a lot of space right here. I want to share some vocabulary with you. Take a look at this big square root symbol. What is the symbol itself called? It's called the radical symbol, just like from the 80s. Radical, man. Did any of you ever say radical? Something was cool? No? Come on, some of you? I used to say radical. Uh-oh. Well, have you heard the fact that radical was something that was cool? Yeah, okay. So that's the radical symbol. This number inside is called the radicand. And then the number that's inside the square root. What's that invisible number right there? It's actually a 2 because this is a square root. It's the opposite of squaring a number. It's a square root. Just to contrast that real quick, if I was doing x cubed, the opposite of x cubed is cube root. So cubing and cube rooting are opposites. Squaring and square rooting are opposites. That's pretty interesting. Normally, normally when we have an invisible number, what is it? A 1. This is the first time we've ever seen an invisible number that wasn't a 1. Isn't that fun? This invisible number is a 2. If you don't see a number there, it's a 2. That number is called the index, the root index. And now I can share with you one of my favorite t-shirt ideas. This is my t-shirt idea. Someday I'll actually make this t-shirt and wear it to school. It'll be super fun. So I would want a t-shirt that says that, and then, ha-ha! Radicant! Because the radicand is -1 and you can't square root a negative number because you can't square root a negative number. So anyway, that's my if I made a t-shirt for everybody that said radicant, would you all wear it? I know you would. I know you would. It's a cool shirt idea. All right. So there we have it, folks. For the rest of this chapter, we cannot square root negative numbers. I know that you probably have learned about imaginary numbers in the past, where the square root of -1 is actually equal to I, but we're not going to use that in this class. You'll use that in maybe Math 150 or Math 140, but in this class, when we see the square root of a negative number, we just say it's undefined, that there's no solution. Okay, let's get going, folks. Number 6. Find the decimal approximation to 3 decimals. Everyone, I want to make sure you can use your calculator, so go ahead and use your calculator to do root 2, root 65, and cube root 63. I'll need to show you how to do that on your calculator. So maybe you will shout out the answer, or give me it very loudly. What is the square root of 2 to at least 5 decimals? How about Emily? What did you get? What's the square root of 2 to at least 5 decimals?
1.4142.
Okay. And then what's the square root of 65 to at least 5 decimals? Jesus, what'd you get? Well, just tell me those 3. 0.62? Okay. Okay, so folks, I'm going to teach you another rule. Okay, here's another rule. You want to write it down. And that is, that anytime you have a number raised or being square rooted, that's the same as raising that number to the power of 1/2. Have we already done that? We already done that in this class? I don't think we have. Yeah, square rooting by definition is x to the 1/2 power. So everyone, I'd like you to try that now on these two numbers. I want you to calculate 2 to the 1/2 and see what you get, and calculate 65 to the 1/2 and see what you get. You should get the same answer. Most importantly though, when you type it into your calculator, it's very important that you do x to the power of parenthesis 1 divided by 2 parenthesis. Your calculator might give you an error if you don't do that. So it's got to be x to the power of 1/2. If you wanted to, you could also do x to the power of 0.5, but that won't be as useful later on. So I'd like you to learn how to do x to the power of 1/2. Did it work, Eduardo? Okay, super. Did you get the same answer? Okay, does anyone need to see how to use their calculator to get this to work? Yes. Well, yeah, your calculator is different. So you'll do that. Oh yeah, it works. Okay. Yeah, just like that. Everybody else, is your calculator working? Yeah. Is it seriously? No. Well, here's the thing, you do the square root and then you also do the power. You just want to do one. So you do 2 to the power of parentheses 1. Got that out. Did it work really yet? Vanessa? There? Ariana? Did it work? Stephanie? Okay. Jasmine? Kim? Jasmine? Lenny? Oh no. Mine's out of battery, so I was on it too. Marlon, did it work? Okay. And Don, did it work?
Yes.
Okay. Okay, so folks, let's all take a guess. If you want to take the cube root of 63, and let's just say your calculator does not have a cube root button, which many of your calculators do not, how do you take the cube root of 63? Raise it to the power of 1/3. Yeah, raise it to the power of 1/3. In general, any root is the same as the unit fraction with that number. So in general, you can say that the nth root of x is equal to x to the 1 over n. It doesn't matter what it is. It could be the 3rd root, 4th root, 5th root. So if you do the 3rd root of 63, what did you get? Did you get? I'm sorry, 97. Okay. Now, folks, what should happen if I take 3.97905 and multiply it times itself 3 times? I should get 63, right? So long as you use enough decimals. How many decimals are in this expression? Technically. Well, that's just the ones that I wrote down. I'm sorry. How many are in reality? Infinitely many. Yeah, there's infinitely many decimals. So you can never actually write down all infinitely many. But if you did, and you multiplied it times itself 3 times, you'd get 63. Okay. Here's a couple challenge questions for you folks. These are challenging. These are tricky. You can share them with your friends and stump your family and loved ones. What's the first root of 7? What? It is 7. Because remember, according to our formula, whatever nth root you want to do, so the nth root of x is just x to the 1 over n. So the first root is just x to the 1 over 1. So this is really just 7 to the 1 over 1, which is just 7 to the 1, which is 7. So that's kind of hilarious. The first root of anything is just equal to itself. So does the first root really mean anything? No, it just means itself. Okay, here's your bonus question. What's the 0th root of 7? 0? Undefined. It's not 0. Is it undefined? Are you all just guessing, or are you using the formula?
1 over 0.
Yeah, because that's 7 to the 1 over 0, and 1 over 0 is undefined, so the whole thing is undefined. Yeah, it's undefined. So you can't 0th root anything. 0th rooting doesn't mean anything. Okay, so there we go, some nice definitions. The next one, number 9, says find the decimal approximation. How do you find the 4th root of 84? 84 to the 1/4. And since 1/4 is easy, if you wanted to, you could do 84 to the 0.25. Right, you could do that as well. You could do 84 to the power of 0.25 because 1/4 is. Did I delete that problem?
Yes.
Oh, okay, sorry. Okay, what happens when you square a square root? So take root 9 right there. What would happen if I squared it?
power 2 and the radical cancel out.
Yeah, they would just cancel out. So let's see here. Oh, darn. That means that all of our numbers are off now, huh? I'm looking at number 10 up here, but you're looking at number...
9.
Oh, no, I'm sorry. Well, if you take root 9 and square it, what happens?
Power 2 and the radical cancel out.
Yeah, they cancel out, which is by definition. Squaring and square rooting are opposites, just like adding and subtracting are opposites, just like multiplying and dividing are opposites. So you could draw a line through the root and draw a line through the square, and it's just 9. Now, folks, real quick bonus question. What's the square root of 13 squared? 13, right? Because the square and the square root would just cancel out. So anytime you see a root and a square together, they're going to cancel. What's the square root of 13 squared? Still 13. Right? Whether you do the root 13 and then square it, or whether you square the 13 and then root it, either way, the root and the square cancel out. Because they happen simultaneously. They happen one after the other, and they cancel each other out. Okay. What do you think the answer would be for the next one? If it's negative root 9, what happens when you square the whole thing? I mean, you might just guess that the answer is 9. And one way you could confirm your guess is actually multiply negative root 9 times negative root 9. What's a negative times a negative? Positive. And what's root 9 times root 9? 9. And you might want to look at that too with your eyes, that root 9 times root 9, that's the same thing as root 9 squared. And if root 9 squared cancels out to 9, so does root 9 times root 9 is just 9. Same thing goes, what's root 13 times root 13? Just 13. Because root 13 times root 13 is technically root 13 squared, and the square root and the square cancel, and you get 13. Right now, we're really learning a lot about just how these symbols work, about the definition of the symbols, how they work, what they mean, maybe some vocabulary. There's a lot. What's that? Oh, okay. Yeah, I mean, there's a lot here. There's a lot of material here. There's a lot of vocabulary here. What about this last one? If I square that whole expression, what do you get? Just 16x squared plus 25. Because if you square the whole thing, the square root and the square cancel out, and you just get 16x squared plus 25. So the main point is that squaring the square root symbol or square rooting a square symbol cancel each other out. All right, so on the next page, I say memorize the squares of the first 20 integers, which I'm really serious about. I think you should spend some time trying to recite those. It might take some time. You might need to write it down. And you might actually need to calculate it. Like, what if you're really stuck on 14 squared? You're like, oh, geez, is it 196? Is it 197? I keep forgetting. One good method to learn it is to actually do 14 times 14. If you actually do that, then 4 times 4 is 16, clear the 1, and then 4 times 1 is 4 plus 1 is 5, and then drop the 0, and then 1 times 4 is 4, 1 times 1 is 1, and then you actually see, oh yeah, it's 196. So that could help you in terms of memorizing these numbers, is actually take the time to multiply it by hand. Okay, so memorize all of those, but then what else do I want you to memorize? The first 5 cubes and 4th powers. So it's already written there for you, but write it down yourself. Write down the cubes and kind of do it in your head. So 1 cubed, that's 1 times 1 times 1 is 1. 2 cubed, 2 times 2 is 4 times 2 is 8. 3 cubed, 3 times 3 is 9 times 3 is 27. 4 cubed, 4 times 4 is 16 times 4 is 64. And then 5 cubed, 5 times 5 is 25 times 5 is 125. You want to be familiar with those numbers. That if you're just walking down the street and you saw 27, you'd say, oh, hey, that's 3 cubed. So work on memorizing those as well. And what about the 4th powers? See, isn't that sad, folks? We go squares, cubes, 4th powers. Wouldn't it be cooler if you call those hypercubes? It would be cooler, it would be cooler. Okay, so what are the 4th powers? One of the 4th is, now how can I get the 4th powers? Just by looking at this list. Because like this is 1 times 1 times 1, so if I multiply it times 1 again, I get 1. And this is 2 times 2 times 2, so if I multiply by 2 again, I get 16. And this is 3 times 3 times 3, so if I multiply by 3 again, I get 81. And then this is 4 times 4 times 4, so if I multiply by 4 again, I get 256. And then 125, I just multiply by 5 one more time, and I get 625. Folks, I'm not saying that any of you should know these things off the top of your head. If you haven't spent any time memorizing these numbers, you don't have any of them memorized. And that's why I'm saying spend some time trying to memorize them. Which means when you're standing in line, waiting for food, or you're driving down the street, have those numbers on your arm, and you just start saying them over and over again. You know, you can actually try to count out on your fingers. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 25. And then when you're walking across campus, you can say 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. I really do honestly expect you guys to work on this. I'm not just joking. Okay. All right. So if you know all that, then can we do the cube root of 64? So here's number, well, it's my number 13. Here's negative the cube root of 64. What's the cube root of 64? Right, it's going to be 4, and there's a negative sign out front, so it's negative 4. Now, first of all, folks, you could just type this into your calculator, right? Because the cube root is really 64 to the 1/3, so you can always just type that into your calculator and put a negative sign in front. So the answer is negative 4. But ideally, if you have your cubes memorized, you would just come over here to your list of cubes, and you'd say, oh, 64. That's 1, 2, 3, 4 cubed. So the cube root of 64 is 4. And since there was a negative sign out front, the answer is negative 4. What's the cube root of 125? Yeah, and again, if you have your list of cubes handy, you can say, oh, the cube root of 25, that's 1, 2, 3, 4, 5. The cube root of 125 is 5. What's the fourth root of 81? Yeah, you would look at your fourth powers, and you'd say, oh, there's 81, that's 1, 2, 3. So the answer is 3. And so on. Again, folks, if they put a negative sign out front, they're just saying that when you're all done, make your answer negative. So when you're all done taking the fourth root of 256, make your answer negative. That's what they mean there. Okie doke. Folks, I realized that was a lot. Like we've only been, or was it not a lot? I mean, I feel like there was a lot of information about roots that might have gone beyond what you already knew. So it's a lot to think about. All right. I just gave you one of these graphs, right? Okay. So, folks, I'd like us to graph the function root x plus 6. How could we graph that? What's one way we could graph it? What's one way we could graph it? You could just use your graphing calculator. Right? Is that fair? We could all just get on our graphing calculator or go to Desmos, and we could graph it that way. What do you think that graph is going to look like? Will it be a straight line? No, because it's not y equals mx plus b. What will it look like? A what? A diagonal line? But you're saying a line, though? Maybe? Somewhat? Okay. Any guesses on what this square root function will look like? I mean, that's a good starting question right there. Just what does the square root of x look like? There it is, folks. What does it look like? I'm going to zoom out. What is it doing? It's increasing. Is it an asymptote? Is it approaching some number? Or does it just keep increasing and increasing and increasing over time? Yeah, it just keeps increasing, increasing, increasing over time. So what does it look like? Like if you had to give it a name or, describe it in some way, how would you describe it? Anybody? Turn your head to the right. Now what does it look like? Yeah, it looks like half a parabola. And in fact, what if I put in negative square root x? Turn your head to the right. What do you see? That's a whole parabola. So what is the square root function? It's a parabola, but it's facing sideways. So a square root function is just a parabola that has turned sideways on itself. Okay, so watch closely. What happens when I add 6 to the inside of the radical? Whoa. Where did it go? I'm going to do that again. This is the normal. Oops, that's the normal one. This is plus 6. This is plus nothing. This is plus 6. This is plus nothing. Where does it go? It just moves left 6 places? Yeah, that's it. What if instead of writing x plus 6, I wrote minus 6? It would just move over there to the right. And what if instead of inside the square root, what if I add 6 to the outside of the square root? Or what if I minus 6 to the outside of the root? So what's the effect of adding and subtracting numbers? It just shifts it up and down, right and left. Okay, well, so folks, why are there no numbers over here to the left? Why does the graph stop at negative 6? Why does the graph not exist over here? All right, well, I'm going to leave that question with you. Why does the graph not exist over there? Let's go ahead and make a table of values. So we'd like to graph the square root of x plus 6, but we're going to pretend that we don't know what it looks like. And so here's what we're going to do. We're going to make a wrong table of values. I'm going to show you why it's wrong, and then we're going to make a right table of values. But do both with me. Okay, we're going to try it twice. So one way people make a table of values is that they start by just putting a random selection of numbers here from negative to positive. So for instance, for right here, we could go ahead and do, say, let's count by 3s. I could do -9, -6, -3, 0, and 3, 6, 9. So why would I choose those numbers? I'm looking at x values that cover the entire center of the graph. It covers 0, and it shows me a little bit about what's going on to the left, and it shows me a little bit about what's going to the right. So this is a fairly customary way of doing a table of values, is choosing some negative numbers, 0, and some positive numbers, and either counting by 3s or counting by 2s or just counting by 1s, either way. So why would this be a bad approach to this particular problem? We're going to plug in each of these. I suppose if you don't necessarily want to draw this yourself, you can always just watch. But how did my calculations turn out? What's the first one? -9 plus 6 is -3, which is undefined. Okay, well, so that didn't give me a coordinate. It's undefined. What about the next one? -6 plus 6? Well, that's 0. That's a number. That's nice. That worked out. What about -3 plus 6? That's root 3, which is 1.73 something. That didn't turn out very nice. It's this decimal. How am I going to graph that decimal? The next one is root 6. Oh, another decimal. I don't even know what it is. It's going to be like 2.4 or something. What about the next one? Root 3 plus 6? Oh, well, that's root 9. That's 3. That turned out nicely. And on we go. Oh, no, this next one is root 12. I don't know what that is. It's like 3 point something. And then the same thing goes for root 15. That's like 3.9 something. How did my table of values work out? Not very good, right? It's unfortunate. One of the values wasn't even defined. A bunch of them were decimals. Only a couple of them turned out to be whole numbers. So that would be the wrong way to do table of values, is just choosing numbers at random. Now, how could we be strategic? What numbers should we try? What numbers should we try?
Square numbers?
Square numbers would be good. Do you mean square numbers for x?
I'm not sure.
That's okay, that's fine. You can be not sure. We really would like this to be a square number, wouldn't we? Because if x plus 6 was a square number, I could actually square root it and get a nice whole number. Making x a square number doesn't necessarily help us because, like, if I chose 4, 4 plus 6 is 10, but you can't square root 10 even. So what's the first number, what's the first square number in your list, folks? The first square number in your list? 0. The first number that you can actually square root cleanly is 0. How would I make x plus 6 equal to 0? What would x have to be? Negative 6. So negative 6 is a good first choice. What's the next square number in your list? 1. How would I make x plus 6 equal to 1? Negative 5. So that would be a good number to plug in. What's the next square number on your list? 4. How would I make x plus 6 equal to 4? 1 plus 6 equals 4. Negative 2. Yeah, so far I've got some solid numbers up here. These are all numbers that if I plug it in, I'm going to get a square number, which means I can actually square root it. What if I want x plus 6 to equal to 9? What would x have to be? I want this equal to 9. So 3. I want that equal to 16. Oh yeah, 10. Very good. And then I want this equal to 25. 19. Okay, now we have some really good numbers. Those are really good numbers to plug into a table of values. Why are they such good numbers? Because they're going to come out clean and nice and very graphable. So now, if we go ahead and plug all those in, we're going to have a really nice collection of coordinates. That's root 0, which is 0, root 1, which is 1, root 4, which is 2, root 9, which is 3, root 16, which is 4, and root 25, which is 5. Okay, so that worked out much better, but it took a lot of planning, didn't it? That took a lot of initial investment to think, what numbers would I want to plug into my function so that it will equal something nice? All right, well, how do we take all those numbers and graph them? I guess I'll just delete this one now. This sad table of values. How do I graph a table of values?
One at a time.
Yeah, one coordinate at a time. So we have this input, output, that's a coordinate, input, output, that's a coordinate, input, output, that's a coordinate. So I really now have the coordinates negative 6, 0, and negative 5, 1, and negative 2, 2, and 3, 3, and 10, 4, and 19, 5. So now I have all those coordinates. And now all of you folks, you can go ahead and plot those on your graph. Go ahead and make your graph. I don't have graph paper, but I'll just go ahead and make a little one anyway. So negative 1, 2, 4, 5, 6, 0. Negative 3, 5, 1, 2, 3, 10. Good. There you go. Did you all get a graph that looks like that?
Yep.
Oh, good. Well, at least you're working on it. Now, folks, to tell you the truth, you will have a question like this on the test. I'll want to see you build a strategic table of values that gives whole number outputs. And when it comes time to actually graph it, as far as I'm concerned, all you have to do is draw the dots. Right? Like if you made a graph and all you did was just do the table of values and then show me the dots, that's fine by me. What I really want to see is dots. Because you can all still see the graph. Even if it's just dots, you can see where the graph is. What I want to make sure I avoid is I wouldn't want anyone to to do the graph by just going like this. Hi-ya! I don't give no credit for that at all because I don't see any dots. I see nothing, no dots. So that graph would get 0 credit, even though it kind of looks like the right graph. I'll give no credit for that. Whereas this, just a bunch of dots, I'd give full credit for that because it clearly shows me where the coordinates are that you calculated from your table of values. All right, should we take a break? Might as well. So the time is 1:46, so let's start again at 1:56. You're a radicant. What? What does that even mean? Nothing. I'm in the middle of it. I'm not ready to give it back to you today. Very sorry. I can imagine you're excited to give it back. I will give it back to you on Wednesday. Or if you want to come to office hours, I can just, or you have to do yours. Or anybody who comes to office hours. It's not lost, but we can go.
That's funny. Yeah, but I'm just like, oh, okay, yeah.
No problem. Goodbye.
Okay.
Yes. Oh my gosh, that's really nice. I was thinking about how busy life is and how you can talk about big stuff. So I'm in a math class too right now. I feel like all of my spare time is that. I haven't read a book, really watched anything on TV. And like whenever I have spare time, it's just doing that. And like we just moved. So it's like I rush home, I help out with our daughter, I do a couple house projects, and then I work on homework, and then repeat. And it's just,
I know that one. Very well.
it's just crazy.
I agree. I always tell my husband before he changes.
Yep. Oh, and I made the decision not to take summer school.
Me too.
Like, oh, it's gonna be cool.
Nice break.
We'll work with summer school and just get a lot of house projects done.
Especially since you have a
Well, we have a daughter, but my wife is due this summer. So that'll be like the last push to do any last house projects that she wants to get the nursery ready.
Since my kids don't require that kind of attention anymore, so. I don't
How old
have to
are
go
they?
home. I have 24 kids.
Mm.
I don't have to go home and take care of them.
That's nice.
I can imagine doing this weekend.
Yeah, we just had a bunch of people over yesterday, so there were 3 babies.
Mhm.
I mean, that's just wild to see 3 babies. Right? 19 months.
Oh my goodness.
Yeah. She can walk and barely run, and she's starting to talk. You know, work one more.
Oh, yeah. It's fine at that age.
Yeah, they
It's
really-
my kids at that age.
She has just started recently becoming like, you know, like cranky about things. Like she never has been yet. But now, like all of a sudden, we'll do the normal thing. She's like, no, let me down. It's really surprising to see.
Develop personality.
Uh-huh. I want to do it myself,
Mm-hmm.
which I guess is good.
Oh, yeah. Mr. G?
Yeah.
Like the
Oh, it
answer is
doesn't.
like that, okay. So just moments, right?
Yeah, just the graph, yeah. Yeah, I see what you're writing though. You're writing the domain.
Yeah.
The domain would be a bracket right there. Because you can plug in -6.
Just, you know, that's what you want me to see.
Just the graph. Why? Does the instruction say something else?
Well, I'm just looking at the answer here.
Oh, they were saying give the domain, I bet. Did it say that?
Oh.
Oh, start by determining the domain. Ah, okay. I didn't even say what that was.
Okay, folks, let's get started again. And actually, thank you, Don. I want to point something out about that last problem. It said use a table of 6 values. We might have done more than 6. Start by determining the domain. We completely skipped that. What's the domain of a function? It's all allowable inputs. So what am I allowed to plug in for the square root of x plus 6? What is x plus 6 allowed to be, and what is it not allowed to be? For instance, what can't I have inside that square root? A negative number. So I need x plus 6 to be what? Positive or 0. So to find the domain, folks, here's what you do. You say, I want x plus 6 to be greater than or equal to 0. And that's what you do. You just write down a nice little sentence. You say, I want this number underneath the square root sign to be bigger than 0, which means positive, or equal to 0 because I can square root 0. And so from there, you go ahead and just solve x. Therefore, x has to be greater than or equal to -6. Which is why in our table of values, what was the first number we plugged in? -6. And then we started working our way up into positive numbers. So yeah, that would have been a good first step, because that tells you exactly what value to put on your table of values first. And then you could do -7, and then we skipped -8 because it would have caused a decimal. And what values did we do? -6, -7. I'm sorry, not -7. -6, -5, -2. 3, yeah, and so forth. So we didn't do every single number bigger than -6. We skipped around to get just those values that when you plugged them in, you'd get a square number. Do you get it?
I know it's last subject, but if you take -6 on the side, wouldn't you switch the sign?
I did. Oh, that one.
Yes.
That's only if you multiply or divide by a negative number.
Okay.
Yeah, there we just were adding and subtracting.
Okay.
Yeah, it's only if you multiply or divide by a negative. All right. Well, great. Folks, I have a bonus question here. What's the -1th root of 5? What?
-5?
No. What's the definition of a root? So the -1th root of x would be x to the 1 over -1. So this would really be 5 to the power of 1 over -1, which is really 5 to the -1, which is really 1/5. Isn't that a weird one? That's a weird one. Likewise, what's the -1th root of 1? 1. Isn't that weird? Anyway, I'm just sharing that with you because it's fun. Like, these are the definitions. This is the playland of math, of having these strange symbols that have definitions, and you just have to follow the definitions and you get strange results. All right, so folks, here we are on the next one. It says to simplify the root. Now, we're about to do something completely different from what we've been doing all morning. All right. So, we're kind of changing gears a little bit. It says to simplify the root. The first thing I'm going to do, so this whole section right here, I'm going to show you the grouping strategy. This is the grouping strategy. All right? For how to simplify a root. Now remember, what does simplify mean? What kind? Yeah, make numbers smaller. Specifically, make the number inside the root smaller. But what do you notice about these particular roots? Are there any numbers inside? No, they're variables. So this is not like root 20, where you could break 20 into 4 times 5 and split it into 2 pieces and square root one of them and not the other. These are variables. So here's how the grouping strategy works. You take your x squared and you rewrite it as a product of individual factors inside. So this is really x times x. Now, the way this works is, since we are doing a square root, that's an invisible 2 right there, every time you see a pair of the same number inside, you get to circle it and bring it out and put one of them out front. So in this particular case, I had a pair of x's. I get to bring it out front, writing down just one x to represent that pair of x's. And then there's nothing left inside the root, so there is no longer a root, and I'm done. The answer is just x. So the answer is just x. Now that might have looked a little funny, so let me show it with a longer one. Oh boy, and the next one is rather long, but I'm going to show it to you anyway. So what's this fourth root of x to the 32nd? Okay, I understand if you don't want to write this all out, but this would be the fourth root of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 32. Okay, so that's the fourth root of x to the 32nd power. And you look at the index, and I can take out quadruplets. So anytime I see a group of 4 x's, I get to take one of them out front as a representative of that quadruplet. I get to take out that quadruplet, that's another x. I get to take out that quadruplet, that's another x, and so on. So there's another one, and there's another one, and there's another one, and there's another one, and there's the last one. I take all of those x's out of the root, and what's left inside? Nothing, because I took it all out. And so my answer is just x times itself 1, 2, 3, 4, 5, 6, 7, 8 times. The answer is x to the 8. So the fourth root of x to the 32nd is really x to the 8. Yeah, Jesus. Yeah. Yes, you can. Yeah, but I wanted to show it visually as well, so we saw what we were doing. Yeah, you can totally just divide 32 by 4, and that's the correct, that's our next strategy. This grouping strategy is so you can see it. So, for instance, everybody, maybe you can try this next one. If you want to do the cubed root of x to the 21st, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So I've got the cubed root of x to the 21st. And I can take out 1, 2, 3, 4, 5, 6, 7 groups of x. So the answer is x to the 7th. And yeah, to Jesus' point, you can just divide the power by the index, and that will tell you the final answer. Although, yeah, so far so good. None of these show a good example. Can we all just write down an example together real quick? I have one more. I have an example that would make this more clear as to why this is helpful. What if you wanted to take? What if you wanted to take the square root? Everyone, just write this down with me. Of x to the 5th. This would be a great example to kind of clarify this. The square root of x to the 5th. Well, that's really the square root of 1, 2, 3, 4, 5. How many pairs can I take out? Yeah, I can take out that pair. I can take out that pair. So that leaves me with 2 x's now out front of the square root. And what's left inside of it? Just a single x. So now my answer is actually x squared root x. And that would be the correct final answer. The square root of x to the 5th is really x squared root x. And you know what I probably should have done first is give an example of an actual square rootable number. That probably would have been helpful. Let me try that. How about the square root of 72? We did 72 earlier, the square root of 72. The first thing we need to do is break 72 into prime factors. So remember, we did a factor tree for that. 72 is really 8 times 9, which is really 3 times 3, which is really 4 times 2, which is really 2 times 2. So we have 2, 2, 2, 3, 3. So the square root of 72 is really 2, 2, 2, 3, 3. So do we have any pairs that we can take out? We have a couple pairs. I can take out a pair of 2s. So there's a 2 outside now. I can take out a pair of 3's, so there's a 3 outside now, and just the 2 is left behind, and so the answer is 2 times 3 is 6 root 2. Is that the same answer we got before? 6 root 2? Yeah. Okay, so again, this is called the grouping strategy. The grouping strategy is just one way to simplify a root. So how about that last one? We could probably do this last one without writing all of those out. What are we going to do? How many groups of 4 x's are they in there? 9. So the answer would just be x to the 9th, but with a negative sign out front. So the answer is negative x to the 9th. Yeah, negative x to the 9th. Now you might look at the grouping strategy and say, Mr. G, that's insane. I don't want to do it that way. And that's fine. Jesus? What does it say in the back? Where? Oh, negative absolute value of x to the 9th? That's really interesting. Yeah, that one's the absolute value. Let's talk about that later. I'll bring that back up at the end. That's a good point. All right. For now, okay, so that's the grouping strategy. Jesus suggested that you wouldn't have to do the grouping strategy. You can just divide the power by the index. So let's look at that. That's the next couple of questions. Okay. The next strategy is actually dealing with fractional exponents. Now, we've already seen this. I say here, when evaluating fractional exponents, oh, well, we've kind of seen it, but let's write it down and divide it, or define it. Go ahead and write it in your notes. When evaluating fractional exponents, the numerator is the power, and the denominator is the root. So I'm going to go ahead and write in the two words power and root. So right up there in this space, let's do an example. Just, all the way up there in the top. Let's do an example together. What we're saying is, let's say you have the number 8 to the 2/3. 8 to the 2/3. Now already this should feel crazy. Like 8 to the 2/3, what does that even mean? Like 8 to the 1st is equal to 8, and 8 squared is equal to 64, and 8 to the 0 is equal to 1. So what is 8 to the 2/3 equal to? What's your guess? Because 2/3 is between 0 and 1. So the answer has to be between 1 and 8. What do you think the answer will be?
4.
How do you know 4? Okay. Well, maybe you're, all right. So maybe you already, because it's the cube root of 64. Oh, I see what you did there. Yes, but in any case, the answer has to be between 1 and 8, because it's 2/3, which is between 0 and 1. Now that's weird because, like with 8 squared, you multiply 8 times 8. So how do you multiply 8 times itself 2/3 of a time? It doesn't really make sense. But there is a definition, and here's the definition. Write it down. The denominator represents the root index, and the numerator represents the power, or the exponent. And the way we're always going to do this is we're going to take a number that's being raised to a fractional exponent, and the first thing you do is the denominator. You cube root first, so we'll do the cube root of 8, and then you take all that and raise it to the power of the numerator. Okay, it has to go in that order. First you do the denominator, then you do the numerator. Okay, so then what's the cube root of 8? If you remember your cubes, what's the cube root of 8? Just 2. So that gives us 2 squared, which is 4. Okay, so that's it. So the answer was 4, which was between 1 and 8. Sarah?
Okay, why wouldn't you square the number inside the root?
That's a great question. So could you do it the other way? The answer is yes. You could if you wanted to. You could do 8 squared and then cube root it. And that's true, you could. You can go the other way. But now look, 8 squared is now a bigger number, And now you have to cube root 64 rather than cube rooting 8. And we can still do the cube root of 64. What is it? Still 4. But let me perhaps give you a better example that's more illustrative of why you wouldn't want to do that. What if you had 27 to the 4/3? Okay, so you want to take 27 to the 4/3. If you do the denominator first, that's the cube root of 27 being raised to the 4th power. And so the cube root, what? Does that make sense? Why?
Yeah.
Well, I was about to say it anyway, so it's fine that you asked. So the cube root of 27 is what, folks? The cube root of 27 is 3. Is the cube root of 27 is 3? So that's 3 to the 4th. And then 3 to the 4th is, well, 3 to the 4th power is 81. So that gives us 81. Whereas what if we had done it in the other order? What if I had done 27 to the 4th and then cube root? Well, what's 27 to the 4th? My calculator's out of batteries. What's 27 to the 4th? What is it? It is a lot. What is it? 531441? That's it. Yeah, so then cube root that. Well, nobody's doing that off the top of their head. It's a really big number. So what do you want to do first, the denominator or the numerator? Always the denominator. And generally speaking, folks, let's realize why that is. What does a root do to a number? It makes it smaller. Whereas what does an exponent do to a number? It makes it bigger. So you'd always want to do the root before you do the power. So you do the denominator before you do the numerator. Okay, so let's try a couple of these. You'll notice that the very first couple problems, the numerator is always a 1. That's okay, let's try it. So 729 to the 1/2. Again, you might want to write it down the first few times. The denominator is the root, the numerator is the power. You might just want to keep writing that down for a while to remind yourself. The denominator is the root, the numerator is the power. So that means the square root of 729 raised to the power of 1. And what is anything to the power of 1? Itself. So I don't even have to write it down. This is just the square root of 729, which we already agreed upon earlier. That, I didn't write it up here specifically. But the square root of x is defined to be x to the 1/2 power. So what are all, well, yeah, so the 729 to the 1/2 just means the square root of 729. And what is it, by the way? Did anyone calculate it? 27? Okay. Yep. So then what's 64 to the 1/3? Yeah, well, let's define it first. The 3 is the root, so that's the cube root of 64 to the 1st, which to the 1st doesn't change anything. And so the cube root of 64 is 4. Likewise, 81 to the 1/4. Again, the 4 is the root, the 1 is the power. So that gives us the 4th root of 81, which is what, just 3? Yeah. So this is what we already knew. We had already kind of looked at this formula and memorized it, that anything to the 1/n is the same as the nth root. But now we can apply this a little more generally. Now that we know that the numerator can be a number as well, not just a 1. So let's try it. Like well, our numbers are off, but how about 8 to the 4/3? Oh my gosh, is that one I did? No, it's not. So how do you calculate 8 to the 4/3? What does the denominator represent, Kim? The root. And what does the numerator represent, Chris? What does the numerator represent? That's it. The what? What does the numerator represent? The power. Yeah, it's the power that's going to take place on that root. So this is going to be the 3rd root of 8, all raised to the 4th power. And everybody, what's the cube root of 8? Just 2. So that's 2 to the 4th, and then you can multiply that on your fingers. 2, 4, 8, 16, and then the answer is 16. Everybody, go ahead and try 81 to the 5/4 on your own. Remember to write down that the denominator is the root, the numerator is the power, And go ahead and calculate that. So folks, you can all check your answer on your calculator. Just remember when you do 81 to the power of 5/4, you want to use parentheses to make sure that your calculator is doing the right thing. Did anyone get the answer 243?
Yep.
Oh goody, it looks like 243 is correct. Because the fourth root of 81 to the fifth power is 3 to the fifth, which is 244. All right. That's a good thing to note. I've been kind of putting formulas over here. So x to the m over n, where n is the root and m is the power, is the same as the nth root of x all raised to the power of m. Okay. Folks, at the start of today, when I said that this chapter, chapter 9, was about square roots and squaring, did you think that there was that much to say about square roots and squares? No. Yeah, probably not. But we're allowed to do almost anything, aren't we? We can do squares, cubes, fourth powers. We can do square roots, third roots, fourth roots. We can do fractional exponents. We can do negative exponents. Exponents is a whole field in and of itself. You could spend months just studying these things. All right. So how do we apply all of this to fractions? A fractional exponent on a fraction. Isn't this enough to terrify any average American? There's a fear of mathematics in this nation, especially about fractions. And look, a fraction raised to the power of a fraction. Isn't that cool? So what's the first one, folks? Let's show a chain of reasoning. It's negative 25/16 to the power of 1/2. Well, first of all, what does the power of 1/2 really mean? A square root. So this is really the negative square root of 25/16. And how do you square root a fraction? You do the individual roots on the top and the bottom. So you're going to square root the numerator, and you'll square root the denominator. And then since there's a negative sign out front, you just make your final answer negative. So what's our answer? Yeah, negative 5/4. That's a nice chain of reasoning. It's showing step by step, one thing at a time, what you're actually doing. This one's a little different. How is this one different?
Exponent is negative.
Yeah, the exponent is negative. Now, what does a negative exponent mean? I haven't written it over here as a formula, but maybe I should. What does it mean when you have a negative exponent? Yeah, it means reciprocal. So when you have a negative exponent, it means to do the reciprocal of that number, whatever it is, and then change the negative exponent to a positive exponent. So since our exponent is negative, let's do that first. We just take the reciprocal of this fraction, and it becomes 25/81 to the positive 1/2. I realize we probably could have immediately flipped it and wrote the square root symbol, but it's nice to your audience to just do one thing at a time. So they can say, okay, from here to here, we did one thing. We did the reciprocal. Now, from here to here, we did one thing. We changed it to a square root. And then from here to here, we do one thing, which is to take the square root of the numerator and the denominator separately. And then from there to there, you just do the square root. That's what the phrase show your work is really supposed to mean. When you show your work, you demonstrate a chain of reasoning that an audience would be able to follow. That's really your utmost concern, is your audience. Just like you're my audience, and my utmost concern is for you guys. Yeah. Uh-oh, what did I do? That's an 81? Thank you. Oops, 81, even better. All right, is that better? Does that work now?
Yeah.
Okay, thanks, guys. All right, well, there we go. We got the whole thing. Now, folks, this next one is a trick question. It's a trick question. But you see, you might not realize immediately that it's a trick question, which is why you just have to start doing the process. So what's the first thing we would do? The negative or the 1/2? I would say the negative, to do the reciprocal of that number, right? So let's do the reciprocal. So now that's negative 9/64, all to the 1/2. Okay, what's the next thing we do? Square root it. So we'll square root the whole thing. So that's the square root of negative 9/64. And then what would we do? Yep, square root both of them individually. So now we have root negative 9, root 64. And then? I think I just heard someone say it. You what, Jesus? You can't square root a negative and the whole thing is undefined. You can't square root negative 9. If you type that in your calculator, the square root of negative 9, you would say error, undefined, imaginary, not real. And so the whole thing you can't do. Which, perhaps, right at get-go, we might have known that because, negative just means do the reciprocal. The reciprocal of a negative number is still negative. And then you're going to square root a negative number. That's not possible. So that particular problem was a trick question. All right. All right, next batch of problems. Simplify by first, these are all just different skills, right? That's what we do in here. We march through a series of skills and definitions and learn them as we go. So, simplify by first converting to rational exponents. Assume all variables represent positive real numbers. Give the answer in radical form. Okay, so the square root of 2 to the 4th. The way I already showed you to do this was the grouping strategy. And so if you wanted to, you could turn this into 2 times 2 times 2 times 2. And every time you have a pair, you can bring it out. And so I brought out a single 2, another 2. So now the answer is 2 times 2, which is 4. That was the grouping strategy. But as Jesus mentioned, you could just take the power and divide it by the index. The legitimate way of doing that is to rewrite this as a fractional exponent. So everybody write this with me. The square root of 2 to the 4th, that's the root, that's the power. How do you write it as a fractional exponent? Remember, the top is the power, and the denominator is the root. So what do I put in there for that fraction? Yeah, 4 over 2. So this is really 2 to the 4 halves. That's the definition. The index of the root was the denominator. The power on the number is the numerator. And you could even write that in there. You could write denominator right there and write numerator right here to kind of remind yourself that the root is the denominator and the power is the numerator. And so what is this? 2 to the 2 is 4 halves is 2, so it's 4. So you get the same answer either way. This is definitely easier than doing the grouping strategy because the grouping strategy can be laborious. Writing it all out and then circling your pairs or your triplets. So how about this next one? The cube root of 2 to the 6th. Again, I really recommend it, at least for the first few problems, you write down denominator out here and numerator in there to build that muscle memory so that you remember that. So how do I write this down? 2 to the power of, Emily? 2 to the power of, it's going to be a fraction.
Oh,
6/3. Yep. So that's really 2 to the 6/3. And 6 divided by 3 is really 2, so that answer is also 4. Okay, I'm going to call on some folks to do these next few. We want to do the square root of w to the 50th. So what's the little invisible number there, Eduardo? That's 2. And then, Mick, what's the numerator? 50. And then, Genesis, what's the denominator? Yep. And so the answer is just w to the 25th. And that makes sense if you think about the grouping strategy. How many w's are underneath the square root? 50. And how many pairs are there? 25. So there are 25 pairs of w's underneath the square root symbol. Sarah, did you have a question?
Oh, that one's not on our
It's not? Oh my gosh. Well, which ones are?
first and the last 2.
Okay, well then z to the 20th. Yeah, everybody go ahead and do these last 2 on your own. Go ahead, do the square root of z to the 20th by rewriting it as a fractional exponent, and then rewrite the last one by rewriting it as a fractional exponent. So let's see here, JR, what did you get? Z to the, 20 halves or 10. All right. And then Leslie, what did you get for the last one? X to the, X to the 12/3, which is, super. All right, folks. Now again, lots of rules. These are lots of different rules about how to manipulate expressions. All right. This next batch of questions asks us to remember our exponent rules from, what chapter is this? Yeah, this was back in chapter 5. Yeah, I think this was chapter 5. It was a little bit ago. So let's remind ourselves about all of our exponent rules. For number, well, the first one there, do you remember what's a to the x times a to the y?
Yeah, plus 1.
Yeah, a to the x plus y. So that first one is a product rule for exponents. So when you multiply two numbers with the same base, you add the exponents. So in this first example, we have x to the 1/4. Oh, I write that down, by the way, folks. Write down the rule, the formula, and then write down our specific problem. So a to the x times a to the y is really a to the x plus y. So here we have x to the 1/4 times x to the 3/4. And so what will that be?
1/4.
Yeah, you could write down if you want to 1/4 plus 3/4, but I'm imagining you can all do that in your head. So it's x to the 4/4, which is really x to the 1, which is just x. Now you don't have to write down all of that, but I really do try to model what a chain of reasoning looks like that an audience could follow. You do one step at a time. Here you just add the exponents, then you actually do add them, then you simplify them, then you realize 1 doesn't matter, and you just write down x. So that's the product rule. Do you remember the quotient rule? A to the x divided by a to the y equals a to the x minus y. So now we can say y to the 9/8 over y to the 5/8. Go ahead and do that one, folks. What did we get? Yeah, the square root of y, because it'd be y to the 9/8 minus 5/8, which is really 9 to the 4/8, which is really 9 to the 1/2, which is really the square root of y. By definition, because raising something to the 1/2 is the same as the square root. Now, honestly, both of those answers are correct, but which one do you think looks better? I think the square root of y, because most Americans know what a square root is. Okay, we all got out of high school knowing and recognizing a square root symbol. Do most Americans know what something to the 1/2 is? No. Definitely not. So definitely that's the better final answer because it's more audience friendly. You might say, audience friendly? If you want to be audience friendly, don't do math. But no, come on, guys. That's not nice. All right, how about the last one? The final rule to remember is that a to the x to the power of y. What happens when you raise an exponent to an exponent? You multiply them, so that's just a to the xy. So in this particular problem, we have b cubed to the 7/8. Yes, that's hey, that's even better. All right, so now we have to multiply. So what should I do to this number 3? Yeah, put it over 1. So now this is really b to the 21/3, which is just b to the 7s. I feel like a lot of this is just symbolic manipulation. Like we're given a problem and then we just manipulate it until we get an answer. Sarah?
So on that one, could we just cancel the freeze?
Yeah, you
With
can do
7?
that too.
Okay.
Sure, both of those are just fine. So long as you draw that line through it. Yeah, that'd be good for your audience. Okay, and then how about that last one, folks? We've got x to the 4th over y to the -8, all to the 1/4. What could we do first? What, man? Oh, you're talking to Eduardo. Okay. Jesus? No. Was someone saying something, Daniel? Yeah, bring up the -8. I think that's a good idea. Remember, negative exponent, other than meaning reciprocal, also means push from the numerator to the denominator or vice versa. So we could rewrite this now as x to the 4th, y to the 8th, all to the 1/4 power. And then how do we bring that 1/4 inside onto both of those? Like imagine it was just y to the 8th to the 1/4. What would you do? You'd multiply, right? So because that's the rule, a power to a power, you multiply the power. So that's y to the 8th to the 1/4. So you'd multiply 8 times 1/4. But we have two things inside. And so you do that to both of them. You'd multiply the 1/4 times the 4. You multiply the 1/4 times the 8. So now we have x to the 4/4, y to the 8/4, and those simplify to just x to the 1st and y squared. So like I said, I feel like so far in this class, other than learning some interesting things about like squaring, cubing, and where the words come from, and talking about memorizing our cubes and our fourth powers and our squares, and talking about approximating to 1 decimal, and talking about simplifying, and talking about what all these root formulas mean and what their definitions are, largely we've done a lot of just symbolic manipulation. So now, finally, we've got a couple problems here that are real-life problems, as in actual real-world scenarios where the formula uses a root. So to solve the problem in the real world, you actually need a root in there somewhere. All right, so these are fairly fun problems. Let's take a look at the first one. Police officers investigating an accident scene can determine the actual speed of the vehicle involved by using the length of the skid mark on the pavement. So first of all, has it ever occurred to any of you that if you got in an accident, you would just lie about how fast you were going? Like maybe it's occurred to you, maybe it hasn't. You're like, oh, I was only going 30. Is that going to work out?
No.
No, because why? They can figure out how fast you were going. You know, probably 99% of the time, they're going to figure out how fast you were actually going. How do they know how fast you were going? I mean, one way is the skid mark on the ground, right? So like if you slam on your brakes and then it shows your skid mark as you're like screeching to a halt trying to not hit somebody, they can look at the skid mark and calculate how long that is. Of course, that's not foolproof, right? Because if you're about to hit somebody and you slam on the brakes, your skid mark will only be very short because you were about to hit them. So that wouldn't tell them how fast you were going. Then how would they know how fast you were going? The what? Yeah, the actual damage, right? Like if your car is totaled, that indicates that you were going very, very fast. Whereas if you just have a little bump on your bumper, you weren't going all that fast. But what are you laughing at?
I don't know what she's laughing at.
Genesis, what are you laughing about?
No,
Did you actually try to lie about how fast you were going once?
no. I always speed, but no.
About your speed?
I always speed. Like,
Oh, you do? Okay. Everybody, Genesis is leaving the parking lot later today. I would avoid. No, I'm just kidding, Genesis. Okay. Well, so anyway, lying is not really an option, folks, because for the most part, police can figure out how fast you're going. So that's what they're saying here, is that they can look at your skid mark and then calculate your speed. Isn't that fun? So let's try it. Everybody write this down, fresh. They can calculate your speed, which is equal to S times M over L to the 1/2. Now, what on earth do all those letters mean? This is not very intuitive, but it says S is the test car speed, and L is the test skid length. So you know what they did, and this would have been a fun job to have. They said, hey, Bob, go over to that big parking lot, get going up to 50, and then slam on your brakes, and we'll measure how long your skid mark was. And then, Bob, go back out, get up to 60, slam on your brakes, we'll measure how long your skid mark was. And then they did that over and over and over again. Can you imagine what a great day that was for Bob? Just getting to go out there, speed, and then slam on your brakes. So they get all this data about how long skid marks are when you slam on your brakes, and that's what the S and the L represent. All right, those are data. That's data. And then what? To find the actual speed S, this is your actual speed, in an accident which left a skid mark M. So M is your actual skid mark. You might want to write that in, just so you know. M is your skid mark, and L and S were both test values from Bob, or from the person who actually went out and did all those skid marks. And then finally, what does the exponent of 1/2 mean? Square root. Okay, so let's find out. Our speed was, capital S was 63 miles per hour. That was the test speed. Your skid mark was 150 feet, and the test skid mark was 100. So let's know what that means. For the person, Bob, who was going 63 miles per hour, he left a skid mark of 100 feet. So if you went 63 miles per hour, you'd leave a skid mark of 100 feet. We want to know The speed, if your skid mark was 150 feet. So now all of this is just a matter of typing it into your calculator. That's really the square root of 150 over 100. So everybody go ahead and just calculate that on your calculator. Make sure you're careful with your parentheses that 63 times the square root of 150 parenthesis divided by 100 parenthesis. Now, one thing to keep in mind, what answer did you get? $77.15. Okay. So 77 miles per hour. Now, does that guarantee that you are going 77 miles per hour? Maybe, maybe not. I mean, your skid mark, maybe you actually slowed yourself down a little bit before the skidding started. Right? So theoretically, you could have been going faster than that. All that really means is that's how fast you were going the minute your brakes locked up and the skidding started. What else? Maybe your vehicle was heavier or lighter, and so it dragged further or not as far, depending on your momentum. So is this value a promise? Is it a guarantee? No, it's just a rough ballpark. But you can bet that the police and the court system will try to use that against you because that's their calculation. Could you argue it? Yeah, you could. You could. You know, probably not just by throwing down and being like, your math is flawed. But, you know, you'd have to give some good explanation. All right, so there we go. That's one formula. How about the next one? This one's really fun. A formula for calculating the distance a person can see from an airplane to the horizon on a clear day is d of x, write it down from scratch, equals 1.22 x to the 1/2. This is the distance you can see from your airplane window to the horizon on a clear day with no clouds. And they're saying x is the altitude of the plane, so draw that in, that's your altitude. And what is the output going to be? What are we calculating? Oh, and by the way, altitude in feet. X is the altitude of the plane in feet, so altitude in feet. Whereas what we're actually calculating is d given in miles. Distance in miles. So there we go. So if you know how high the plane is flying, you can calculate how far away you can see. And yes, the formula is really quite simple. It's just 1.22 the square root of x. And that's going to give you a fairly good calculation about how far you can see from your airplane window. So folks, take a guess. How high do planes normally fly? When you're on an airplane and the captain comes on and says, hello, we'll be flying at X feet. Do you remember how many feet he said, or she? Anyone know how high you are in a plane? 30,000 feet, maybe 25,000 feet. Yeah, somewhere in that window, 25 to 30,000 feet. So let's just see, 25 to 30,000 feet, which would be easier to calculate, 25,000 or 30,000? I mean, maybe actually neither, because I was going to use the math magician trick. 25,000, that would be 25 times 1,000. You can't square root 1,000. So either one. Let's just go ahead and say you're cruising at 30,000 feet. Let's go ahead and calculate it real quick. If you're cruising at 30,000 feet, then go ahead and calculate 1.22 times the square root of 30,000. What is the square root of 30,000 times 1.22? What is it? 21 what? 211.3? Well, that's fine. That's fine. Okay, but it was 211? Did I hear you correctly? Okay. Okay, so what is that, miles? Okay, folks, this formula I'm pretty sure is correct. Like, it's a real formula. So look what that means. If you're flying over Phoenix Okay, so there you are, you're flying over Phoenix. Here's my really good drawing of Arizona. And here's Phoenix. So you're flying over Phoenix in a typical airplane on a typical day, flying at 30,000 square feet. How far can you see in all directions? 211 miles. Can you even imagine? So that means on the horizon, can you see Tucson? How far away is Tucson? Like 110 miles, depending on where you're going from in Phoenix, but like 100 something. How far away is Flagstaff? Isn't it like 180, 190 miles? So check out how fun that is. If you were flying over Phoenix at cruising altitude and you looked out the window and you looked at the horizon, okay, way off at the horizon, could you barely see Tucson? Yeah, absolutely. You've got a radius of 200 miles. Could you see Flagstaff? Yeah, like how cool is that to think that all you have to do is be flying over Phoenix and you can see Tucson and Flagstaff simultaneously, way off in the distance on the horizon. That's pretty cool. Okay, we didn't even do the actual problem. What was the actual problem?
17.
Yeah, 17,000 square feet. Okay, well, all of you can do that. You just plug in 17,000 and you get 1.22 times 17,000. And what's the answer? 159. Okay, well, hey, 159.07, 159 miles. Can you still see to Tucson? Yeah, can you still see to Flagstaff?
No.
Not quite, but pretty close. Number 42, everyone can just cross that out because I think it's a terrible problem.
39.
Oh yeah, or 39, yeah, that next one. Well, folks, we're moving right along. Was this our first day of chapter 9?
Yes.
Yeah, okay, well, we did great, folks. So I don't think I have anything to hand back to you. I'm about halfway through grading your tests. So I'll give them back to you on Wednesday. And that's all I have for you. If you have any questions, please come see me in office hours. I'm always happy to help. This is the definition of a negative exponent. Anytime you have a negative exponent, if it's in the denominator, you put it in the numerator. It's not exactly. Good question. That's me.
Sorry,
Manuel, why are you sorry?
I'm always falling asleep.
Well, not always. Normally just once or twice a class.